Now that we've developed the notion of a sigma field, we can proceed to formally define measure spaces. To begin, we start with any set omega, our sample space, and we equip it with a sigma field over omega, a sigma field of subsets of omega. It could be 2 to the omega, the sigma field of all subsets. Most likely it is a proper subset of 2 to the omega, but must be a sigma field. We call such a pair a measurable space. The elements of the sigma field in this setting are known as measurable sets. In a probabilistic setting, we will also call them events. Now, if they're going to be measurable, then we should be able to measure them. And thus we define the notion of a measure. A measure is a function defined on the sigma field in a measurable space. It takes in measurable sets and spits out positive numbers, non-negative numbers, and possibly infinity. We do allow measures to take infinite values. Not every such function is okay, as we've motivated from the beginning. The critical feature of measures is that they are countably additive. That is, if we have a countably infinite sequence, or finite sequence, of disjoint events, disjoint measurable sets in the sigma field, then the measure of the disjoint union of those sets must be equal to the sum of their individual measures. If we have such a function on a measurable space, then the triple, omega f mu, is known as a measure space. There are a few special kinds of measure spaces that we will primarily be concerned with. If infinity is just not allowed, and all sets in F, including omega itself, have finite measure, then we call the space a finite measure space. A special case of that, the one most relevant to us, is when the total measure of the full sample space, omega, is 1. Then we call the measure space a probability space, and we call the measure a probability measure. Those are the ones that are, of course, of most interest to us in this course, but we will need the theory beyond just probability measures in order to construct and understand probability measures. Let's look at some simple examples to begin. For starters, here are the stupidest examples. The uniformly zero measure, which assigns measure 0 to all measurable sets. This is vacuously countably additive. Similarly, we could assign measure infinity to all measurable sets, since any sum of infinite numbers is infinite. How about a more interesting example? Point masses. Here we start with the full sigma field of all subsets of any given set that we wish to start with, and fix some point in the underlying set omega. Then we can define a measure, which we usually denote by delta, as follows. For any subset, E, we define the measure delta of E to be 1 if the specified point is in E, and 0 if it is not. This is a perfectly well-defined formula for the set function delta on all of 2 to the omega. And it manifestly takes values in 0 up to infinity. In fact, it only takes 2 possible values, 0 and 1. So to verify that it is a bona fide measure, we need to check only that it is countably additive. This is, of course, always the hardest part, but in this case, it's not so hard, owing to the following observation. If I have any countably infinite or finite disjoint family of measurable sets, of subsets of omega, then the specified point is in at most one of those disjoint sets. If it's in one, it can't be in any of the others, because they're disjoint. It might, however, fail to be in any of them. So let's deal with those two cases. Suppose that the point omega naught is in one, let's call it n naught, of the index sets. Then, of course, omega naught is in the union of them all, since it's in at least one of them. And therefore, by definition, the measure of the disjoint union is 1. On the other hand, if I look at the putative sum right here, well, this is a sum of infinitely many terms, but at most one of them will be non-zero. I'll get 0 plus 0 plus 0 plus eventually I'll get to the n naught position, and that will give me a 1, because omega naught is in E n naught. And then the rest will be 0. And of course that sum will be 1. And so I get agreement in that case between the measure of the disjoint union and the sum of the measures of the individual pieces. Now let's check the other case. What if there is no n for which omega naught is in En? Omega naught is not in any of the sets. Well then, it's not in the union of the sets, and therefore, by definition, the measure of the union is 0. And similarly, since it's not in any of the sets, all of the terms here, the measure of En, are 0, and so that's a sum of 0, which is 0. Therefore, we have agreement. Delta is a countably additive function on the sigma field, taking values between 0 and infinity, and therefore it is indeed a measure. In fact, it's a probability measure because the total mass of the set is 1, since no matter what point omega naught we chose, it must be in the base set. This kind of point mass is one of the basic measures that we will encounter over and over in our study of probability theory, but it is very far from the most interesting or most general case. Before proceeding to try to construct some fundamentally different measures from this discrete case, let's talk about using it to build some more general measures, and in general, building new measures from old ones. Let's start with a measurable space, and suppose that we have already produced a measure, mu, for example, a point mass like the one we just constructed. One thing we can do is scale it, multiply the measure by any non-negative number alpha to produce a new measure. To be clear, what this means is that the measure alpha mu eats any measurable set in the sigma field F, and it spits out the value alpha times the mu measure of E. That produces a new measure whose total mass is alpha times the total mass of mu. We can also add measures up. Indeed, the key characteristic of measures is an additivity, and therefore adding them is going to work fine due to the associativity and commutativity of addition. If I take a countably infinite or finite sequence of measures, then I can take the sum of them and produce a new measure. And let me just make a few comments about that. All of the measures are non-negative in value, and they're allowed to take infinite values, measures are in general. And therefore, there are no convergence issues here with this potentially infinite sum. This sum could be infinite, or it could be finite, but it won't oscillate in between some values as we take the sum higher and higher because it is a sum of positive functions. So this makes perfect sense as a function, and once again, our only task is to verify that it is indeed countably additive. So let's do that right now. We need to check that for any disjoint countable family of events in our sigma field, this mu sum measure of the disjoint union is the sum of the individual measures? Well, for starters, the measure mu of this disjoint union is, by definition, right here, the sum of the mu j measures of that disjoint union. Now, inside that outer sum, we use the fact that mu j is assumed to be a measure. And therefore, we have an inner sum over I of the sum of mu j of the pieces EI. That's from the definition of mu j being a measure. And now we just need to do a switcheroo. We reverse the order of summation in this double sum. First summing over j, and then summing over I. Now, you should be very skeptical of arbitrarily reversing summations. It's not always true. But again, because of the positivity of all terms involved, reversing the order of summation is legal and fine here. In fact, it goes under the name of Tonelli's theorem from undergraduate analysis. And now we're in good shape, because this inside sum is exactly the definition of mu of EI. And we see that we have indeed verified that the mu measure of the disjoint sum is the sum of the mu measure of the individual terms, verifying that mu is a countably additive measure. We can use this to put together point masses to form a more general discrete measure, like this. Fix some collection of points omega j in the sample space, and fix some positive weights pj, and then define mu to be the sum of the scaled measures pj times delta of omega j. Now, pj times delta of omega j is a measure, and this is a countably infinite sum of measures. Therefore, it is a measure by what we just proved. If we arrange for the weights pj to add up to 1, then mu becomes a probability measure. Indeed, the measure of the full space omega will, by definition, equal the sum of pj times delta omega j of the full space omega. Of course, each point omega j is in omega, and so this is always 1. So this becomes the sum of the pj's, which, by our assumption here, is 1. And so we get a total mass 1 measure, a probability measure. Now, in the special case where the sample space omega consisted of the specified points omega j, that is, if omega is a countable set, then this is the entire complete arena of discrete probability. We could give an alternative description of how such probability measures work simply by noting that for any set E in the sigma field, its measure is the sum, as written here, but let's write that in a different way. This is the sum over all of those indices j for which the point omega j is in E of pj. Or alternatively, we can write this as the sum over all points in E, a sum which makes perfect sense because E, being a subset of a countable set, is countable, of the measure of the singleton omega, which is just pj if omega is equal to omega j. Discrete probability is a rich field with applications throughout mathematics and science. But it's not enough for us. We need to move beyond the discrete, and that's going to take some more work. Before we get there, let's just highlight a few elementary properties of measures that follow from the definition. Measures are always monotone. That means that if I have two measurable sets A and B, where A is contained in B, then the measure of A is less than or equal to the measure of B. Why is that? For the following simple reason. A is contained in B. That means we can write B as B minus A union A. And this union is, of course, a discrete union, because B minus A excludes all of A. Therefore, by even finite additivity of the measure mu, the measure of B is equal to the measure of B minus A plus the measure of A. Now, I don't know what the measure of B minus A is, but whatever it is, it's a non-negative number. And therefore, this is greater than or equal to the measure of A. Similarly, we have what is sometimes known colloquially as the rule of addition. If I have any two measurable sets, A and B, then the measure of A union B plus the measure of A intersect B is the same as the measure of A plus the measure of B. And we can see this pictorially as follows. Let's try to compute the measure of A union B. That's here in the picture. I could compute that as the measure of A plus the measure of B. The problem is that the region in the middle got covered twice. And so in order to get a correct equation, I have to subtract one of them, saying that the measure of A union B is equal to the measure of A plus the measure of B minus one copy of the measure of the intersection, which is exactly what that equation says. You can take this schematic and convert it into a proof using naive set theory right away. And finally, let's note that measures are subadditive, which may sound strange considering that we are insisting they be countably additive, but this means something slightly different. It means that if I take the measure of the countable union of any collection of measurable sets, whether they're disjoint or not, then the result is less than or equal to the sum of the individual measures. Why is that? The idea is to reconstitute the union of the BNs as a disjoint union of some related sets, and thus leverage the countable additivity of the measure mu. Define A1 to be B1, A2 to be B2 minus B1, and in general, let AN equal Bn minus the union of all of the previous Bs. By construction, these are disjoint sets. Moreover, the way we've constructed them, by taking out the previous Bs as we go, we've arranged it so that the union of any finite collection of the A's is the same as the union of the same number of terms of the B's. And therefore, that holds for the infinite union as well. Thus, we can simply compute that the measure of the union of the B's is the same as the measure of the union of the A's. Now the A's are disjoint, as I noted over here, and therefore this is the sum of the measures of the individual A's. But we also note from the definition that each AN is achieved from Bn by removing some pieces, and therefore AN is contained in Bn. And so we can use the monotonicity property to show that this sum is less than the sum of the measures of the BNs, which is exactly what we were hoping to demonstrate. There are other basic properties of measures that we may need as we go. But first, we need to turn our attention to constructing more general measures, which is a much harder task. And in fact, we're going to have to lower our expectations at the start. Instead of constructing measures, we're going to construct weaker objects called pre-measures and finitely additive measures that we will later figure out how to extend to full-fledged measures.